In this lecture, we will be covering the autoregressive conditional heteroscedasticity of order Q, or ARCH-Q process. First, let's recall the definition of the ARCH-1 process. We have a epsilon t white noise process. Note that it's a white noise with variance 1. In such a case, we define the process AT as an autoregressive conditional heteroscedasticity 1, or ARCH-1 process, if we have the following defining equation for parameters alpha naught and alpha 1 that are non-negative, and alpha 1 less than 1, so that we have a finite variance for AT and stationarity of AT. Note that the easier way to understand this defining equation is to square both sides, and we get this expression 2 here. And we note that this is like an AR1 process for the square of AT. So like an AR1 process, recall that in AR1, say YT, we would have YT minus its mean is phi times YT minus 1 minus its mean plus a noise term. And maybe we'll call it something different because the noise term, call it epsilon tilde, in this case is not a standard noise term. It doesn't have a variance of 1. But the idea here is that YT differs from its mean at time t with a memory piece of how it differed from its mean in the previous time step plus a noise term. If we think of mu being 0, so a mean 0 AR1, then in that case we see that this expression is very similar to this expression in that you have the process at time t remembers a piece of itself from the previous time step. And then you have the effect of noise in the AR1. It's additive noise. In the ARCH-1 process for AT square, you have that memory parameter from the previous time step, but the noise term is multiplicative. So this is like an AR1 for AT square, but the difference is multiplicative noise. And if we recall some of the properties of the ARCH-1, here's our defining equation repeated. We have a mean of 0, and we also have a conditional mean. So conditional on knowing the past values of the ARCH-1 process. Our expectation, given that information, is 0. So we can think of this as knowing the past values of the ARCH process. They don't help us guess at the current value. The guess at the current value knowing the past is 0, which is the same as the guess at AT without any extra information. In the case when alpha is less than 1, we have a variance of alpha naught over 1 minus alpha. And notice that these two properties here, fixed mean and a fixed variance, mean that AT is weakly stationary. So the definition of weakly stationary is that you have a fixed mean and a fixed variance in time. The big change from previous types of processes that you typically study is that the conditional variance is non-constant. So sigma t squared is defined as the variance of AT given the previous values for the A process. And we see that's equal to alpha naught plus alpha 1 times AT minus 1 squared. So we have non-constant conditional variance, which is the defining characteristic of what we call conditional heteroscedasticity. As a result of these four properties, for any lag larger than 0 in size, we have 0 autocovariance. So remember, we're using gamma for our autocovariance. So autocovariance of A is 0, and the autocorrelation is thus also 0. So this means that the ATs are not correlated with each other, but we note, because of our observation that AT square can be written in this expression, which is a lot like an AR1, the key thing to remember is AT square remembers something about AT minus 1 squared. Because of that, these variables, these a sub t and a, say, t minus I, they are dependent. They're uncorrelated, but they are dependent, and the dependency is reflected in the second moment, in a square, where we have a non-zero autocovariance and a non-zero autocorrelation. So the autocorrelation is given by phi to the h. So if we look at this autocorrelation function, and remember this is for the square, we have a graph of this exponential decay. And this is the same autocorrelation as that of an AR1 process. So the ARCH1 process has this cool property that it is weakly stationary, mean 0. It has no autocorrelation, 0 autocorrelation, obviously for lags greater than 0. Autocorrelation with lag 0 is 1. But any other lag, we have no correlation, but we have dependence, and the dependence comes via a square. And that is coming from the non-constant conditional variance. So why is this important? This is important because we're looking for a new candidate for a noise process. If we think about the properties of a noise term, the defining properties, first we have mean 0, and we typically also have that there's no autocorrelation. So your epsilon t's, we usually call them epsilon for our white noise, but our noise process has no autocorrelation, which will mean we have this conditional expectation being 0. Also, a finite variance gives us weak stationarity. So we like a weakly stationary process with no autocorrelation. That makes this AT a good candidate for a noise term. The big difference is this conditional heteroscedasticity property. So this is the key result in how this ARCH1 is going to be different than what we've been using as standard white noise terms. And the key really is the memory. So the conditional variance at time t remembers something from the previous value of the noise process squared. And so remember, this allows you to have regimes of high volatility, high conditional volatility or conditional variance, or low conditional volatility or conditional variance. So if you have a small AT minus 1, AT minus 1 squared is also small, which results in a small conditional variance, and thus a likely small move from the average of 0 of AT at time t. And you can make the same argument if AT minus 1 is large, so is AT minus 1 squared, which results in a large sigma t square, which makes a large deviation from the average of 0 for AT likely. Now we take this idea of the arch1 and we just allow for memory going further into the past, specifically q time steps into the past rather than just 1. So this definition is very similar to the arch1. We have epsilon t being a 0-1 white noise. And we say AT is an autoregressive conditional heteroscedasticity Q, or arch Q process, if AT is sigma t times epsilon t, where we have alpha naught, alpha 1 up to alpha q non-negative, and sigma t is equal to this expression here, which you note is just an expansion of the expression for the arch 1. If q is equal to 1 in this definition, then we have the arch 1 process we were just looking at. So this is allowing memory q time steps in the past to affect the conditional standard deviation or the conditional variance. As we did before, let's take this expression 8 and square both sides of it. So we have 8 written again as 11 here, and when we square both sides, we see that we have AT squared is alpha naught plus the sum of the alpha i's times the AT minus I squares times the epsilon t square. And if we recall, we go back to our autoregressive processes. If we recall our autoregressive of order p process, and let's assume, just to make the notation simpler, that we have a mean 0 process. Then we had yt is equal to the sum. I goes from 1, in this case we'll say q, of phi sub I times y t minus I plus epsilon t. So that was our autoregressive of order, actually we should say of order q, process. And you see, looking at this equation 12, this looks a lot like the ARQ process, except that rather than having the noise be additive, the noise is multiplicative. So just think about these two things thematically. For an ARQ, the process YT has memory for each of the previous values of y going back q time steps. Each one of those has its own memory parameter, phi sub I. So you have this memory expression here, and then you add some new noise. Here, for the arch q, the square of it, we have memory via these alpha i's, remembering the previous values of a squared. But then rather than adding noise, we multiply. And the result is that this will behave like an AR1 in terms of autocorrelation. So we have very similar properties for the arch Q that we saw in the arch 1, which we won't derive here, but if you see the arch 1 lecture, you'll see we did derivations for that. And so AT has 0 autocorrelation for lags greater than 0 in size. And AT has constant unconditional and conditional mean 0. It also has constant unconditional variance. So this means AT is weakly stationary, mean 0, and it has no autocorrelation, which means that it works as a noise term. These are the kinds of properties we want to see in a term that we consider a noise. AT as we were mentioning above, has non-constant conditional variance, so it has that conditional heteroscedasticity that we're looking for. And because of the argument we just made on the previous slide, it has the same autocorrelation function as that of an ARP, or if we want to be syncing things up, we're looking at Q lag. We usually say ARP, that's the standard definition, but in our ARCH terminology, we're looking back at Q. So this makes the ARCH-Q process a good candidate for a noise term. And if we're doing things like, when we say candidate for a noise term, remember what we're talking about. If you're doing something like a regression model, for instance, and you have a response being equal to a function of, say, P predictors, typically we're adding an epsilon t here where epsilon t is white noise. But now we're saying we have a new candidate for that noise term, and it still works nicely as a noise term because it's mean zero, constant unconditional variance, no autocorrelation. It works as a noise term for a regression. But the conditional heteroscedasticity allows for this modeling of changes in the conditional variance in time. Now, one deficiency that we have is we can get high frequency oscillations in the conditional variance. And by that, we mean you can get high volatility. So recall, we often will call the conditional standard deviation the conditional volatility. And so this can come in short bursts. And in reality, this is often not the case. We need to have the ability to model something like you could think of what we would call a regime change model, where you may have a sustained period of high conditional volatility and a sustained period of low conditional volatility. Thinking in terms of a financial example, think about something like a long period of market calm, where asset returns are not varying all that widely, followed by a period of a tumultuous market where asset returns are varying much more widely. But each of these types of regimes sticks around for a while. And so we need something with a little bit more staying power, a little bit more memory. And the fix that we will have for this comes from the insight that if A, say, t minus I is large, that means at time t minus I, A had a large deviation from its mean of zero. Well, if it had a large deviation from its mean of zero, that's going to be reflected in having a large conditional variance at the same time. So AT minus 1 squared being large, it's going to mean that sigma t minus I is also large. And so the fix that we have is we say, well, why don't we let sigma t not only remember something about the previous noise terms, but how about previous values of itself? And that's what leads us to the GARCH model. And the G really stands for nothing more than generalized. So AT is a GARCH PQ process, or a generalized autoregressive conditional heteroscedasticity PQ process if, and note, this definition is simply a modification to the ARCH-Q process definition. So we have the noise term itself, really that's what we care about, this AT, that is equal to sigma t times epsilon t. We have all these parameters, our alphas and our betas, all non-negative. And our sigma t is equal to the following expression, where we have alpha naught plus these memory terms for the AT minus I square. And notice that if you were to, again, just get rid of this term, then what you would have would be the ARCH1 process. So it's the addition of that term that makes it a GARCH process. And here you see we are going back p lags in the past, different than Q. And we have a weight of beta I for each of these previous conditional variances, sigma t minus I square. And so this is the GARCH process. And based on the reasoning that we had on the previous slide, this, having the feedback from both the square of the noise term and the conditional variance, allows us to get more sustainable regimes of high or low conditional standard deviation or conditional variance. And so this will be the focus of the next lecture, which I encourage you to watch, and we will also investigate how you can use this process as a noise term in time series modeling.